Welcome! This is a tutorial on how to adequately prepare and export your 3D models for 3D printing within the context of the model workshop KTH School of Architecture. This is not a tutorial on 3D modeling, so it will not go in depth into topological issues such as non-manifold polysurfaces and open geometries, and will assume that you have prepared your 3D models to be topologically 3D printable, that is, closed and manifold. Nevertheless, we will cover some minor pitfalls later on. The first step is optional but recommended, to first save your Rhino file with only the objects relevant for 3D printing included. This can be done by selecting your 3D printable objects by dragging a window from left to right with only your desired objects completely included, and typing export and hit enter or space to confirm. Make sure that you select a suitable export directory. Choose a relevant file name for your separate 3D printing fabrication file and make sure that it is saved as a rhino.3dm model file. To easily navigate to the export directory in the next step, copy the directory from the export window with Ctrl+C before saving the exported file. In a File Explorer window, paste the directory that you previously copied and hit enter to go to it so that you are in your export directory. Identify your exported file and click and drag it into the Rhino viewport. Choose to open the file. Now we want to move everything close to the model origin to reduce precision errors when the objects are meshed during export later on. Select everything with Ctrl+A and enter the command M for move. Hit space or enter to confirm, and then click on any point of your objects. Activate O-snap to enable snapping. With the point to move from selected, enter 0, which is the same as 0, 0, 0, the origin of the model coordinate system, and press space or enter to confirm the move command. Type and enter the command ZS, that is zoom to selected, and press space or enter to confirm to recenter your camera orbit point to the object's mean center point. The 3D printers use millimeter as their inherent unit for G-code. If you are not already working in millimeters, if you are, you can omit this step, right mouse button click the unit in the lowermost segment and select Unit Settings. Change the model units to millimeters, click OK to confirm, and accept the rescaling of the model so as to make sure that measurements are still 1:1. With all objects selected with Ctrl+A, enter the Scale command. Base point can be set to 0. Scale factor should be set to your intended fabrication scale. In this case, we want the models to be printed in a scale of 1:400, so we type and enter 1 divided by 400. The maximum dimensions per 3D printer workbed is 200 x 200 x 200 millimeters. Create a rectangle with the rectangle command. Choose 0 as your origin point, and then make sure that the length and width are both 200. Type cell last to select the last object, which is your newly created rectangle. If the model or models easily fit within the workbed boundary, there might be no need to refine their placement as long as their bottom surfaces are all horizontal to each other. But if they cannot easily fit, then the following procedure might be recommended to maximize the effective usage of the workbed area. To maximize the effective usage, one might first rotate all objects so that they are as orthographically oriented as possible. Do this by selecting the first object, type and enter rotate, choose a suitable starting point, the vertical axis of which the object will rotate around, make sure ortho and O-snap are both active, select a suitable end point, and choose, by left-clicking, the intended orientation of the object. Repeat this for the remaining objects. Now, select an object, type and enter M for move, choose a bottom corner point, and type 0 to move it to the origin point. Select the next object and do the same, but now move it to a suitable corner of the first object. With gumball active, click the relevant triangular arrow, red for X, green for Y, to move it 2 millimeters away from the first object. This is a sufficient margin for 3D printing. Repeat for the remaining objects. If you have any non-rectilinear geometries, the efficient nesting of objects will of course be more of a non-systematic challenge, but place them in such a way so that there is at least 2 mm margin between the individual objects. In this case, all objects fit within one workbed boundary. If this would not be the case, create more rectangles until you successfully fit all objects within a set amount of workbed boundaries. The pricing is based on the number of used workbeds as well as the amount of material consumed. The actual prices are stated in the description, since they vary over time depending on our actual cost of purchasing. You pay a booking fee per used workbed, which covers the cost of consumables such as glue and nozzles, as well as service fees when the machines are sent to service technicians for repair. You also pay for the material that you use. Before exporting, we will briefly touch upon some pitfalls which may be encountered. 3D printing is a precise fabrication method, but there are some physical limitations when it comes to the reasonable level of detail of your 3D printed objects. To make sure that a given object actually can physically adhere to the workbed and does not come off during printing, it is recommended that its bottom surface is not thinner than 2 mm in width. All bottom surfaces must be completely flat. If it is not, then it will severely affect the workbed adhesion, since the relative adhesion area for the object is reduced significantly. If the geometry allows for it, make sure to rotate the object in any way which utilizes any completely flat surface as its bottom surface. All objects must have their flat bottom surfaces completely horizontal with regards to each other. This is most easily evaluated by doing a bounding box. Press enter again to confirm that you want world coordinate dimensions. And see if there are any model bottom surfaces that is not Z fighting, intermittently clipping through. Z fighting, which you see here, means that the bottom surface of the bounding box is co-aligned to the bottom surface of the object, which is a good thing. It means that they are horizontal to each other. If any model has its surface not Z-fighting, it might mean that it is erroneously placed along the vertical Z-axis. Ctrl Z to undo the bounding box, identify the object, which we previously did. Move, constrain movement to vertical axis, select suitable bottom corner point, and align it to any other else. Now repeat the bounding box. Now that we can see that all bottom surfaces are properly Z-fighting, we can assume that all bottom surfaces are horizontal, which they should be. Ctrl Z to undo the bounding box. Overhangs extending more than 50 degrees will need support geometry generated below to reduce the risk of sagging due to gravity. Cantilever geometry and horizontal elements above void will for the same reason need support geometry as well. If you have a model with many of these overhang sort of like pseudo cantilever geometries, which would create a lot of support geometry underneath that would have to be manually removed, it may be wise to simply rotate this so that you have a flat bottom and no need for support when fabricating this element. Support geometry in itself is nothing problematic. It is automatically generated when we slice the model in the 3D printing software. It leaves the underlying and overlaying surface with a slightly less smooth surface texture and will have to be manually removed with a small plier, tweezers or something of the sort, but make sure that there is a physical possibility to actually remove the support geometry. The best example of what to avoid in this sense is an encapsulated void, which would definitely need support geometry underneath its horizontal ceiling, and where there would be very little physical opportunity to reach a tool within to remove these efficiently. The 3D Slicer software will analyze your 3D model or models and determine what is inside and what is outside for each horizontal layer. Thus, it is important that all your objects are closed and that each object's surfaces constitute a single hull or shell, so that it is totally unambiguous for the slicer software regarding what is inside and what is outside. Your object is closed when there are no openings. Your object is manifold when each individual surface has one pure inside and one pure outside. These 4 examples look harmless enough, but as of now, none can be reliably 3D printed. For this first example, we have an open polysurface. If you type and enter show edges, and you make sure that naked edges are shown here, you can also select non-manifold edges if you have a non-manifold object, and if you have the naked edges option active here, you will see any edge which borders an opening to be highlighted. In this case, we simply lack a bottom surface. Easy enough. We can close this. In this case, we can simply select the object and type cap, since the bottom opening was completely flat. For the second example, it is not a non-manifold object per se, but it showcases a trouble with non-manifold surfaces. If we activate the ghosted view mode here, we see here that this vertical surface extends below the meeting with the oblique surface, which makes the portion below non-manifold, since this surface or this portion of the surface has 2 insides, both sides being inside of the surrounding volume. Here we need to make sure that the object gets a single hull, one set of surfaces unambiguously defining the binary inside and outside. In this case, we can select the inner object, Ctrl-Shift-S to activate the splitting command, select the outer volume here as our cutting object, space or enter to confirm, Ctrl-click the upper part here to remove it from the selection, delete the remains of the selection, then select all of these, or both of these, open polysurfaces and Ctrl-J to join them into one closed solid polysurface. Very good. For this third example, we actually have 2 closed polysurfaces, but they are overlapping each other. Make sure to select both of them and type and enter Boolean union to merge them properly, creating a single closed polysurface. For the fourth and final example, we can switch back to the shaded view mode. This is not a non-manifold object per se either, but it showcases yet another non-manifold surface problem where the surface is not properly aligned to its intended border, instead extending and creating a portion which has 2 outsides. In this case, it might be easiest to simply explode the object into individual surfaces, select the non-manifold surface, Ctrl-Shift-S to activate the splitting command, select the manifold surface which borders the non-manifold surface as the cutting object, space or enter to confirm, Ctrl-click the manifold portion of the non-manifold surface and delete the non-manifold portion. Now select everything again and Ctrl-J to join, and we have one closed polysurface. Very good. This can be 3D printed, along with the other 3 as well. All of them are 4 closed polysurfaces. For 5 of our 6 3D printers, the maximum height is 200 millimeters. For the 6th, it is 300 millimeters. Select all of the objects, type and enter bounding box, and confirm with space and enter yet again that you want the world coordinate dimensions. The third dimension here is the Z axis dimension. Make sure that this does not exceed 200 millimeters for ordinary printing or 300 millimeters for extra high printing, which is extra sensitive to queue times. Press Ctrl and Z to undo the bounding box. When you have made sure that 1. Your objects are close to the coordinate space origin, 2. Your active model unit is millimeter, 3. Everything is scaled to fabrication scale, 4. Everything fits within individual workbed boundaries of 200 times 200 times 200 millimeter. 5. Everything is placed with an inter-object margin of at least 2 millimeters. 6. Thin elements' bottom surfaces, which should adhere to the workbed, are no less wide than 2 millimeters. 7. All bottom surfaces are completely flat. 8. All individual objects have their bottom surfaces horizontal to each other. 9. Overhangs and cantilever geometries are designed in a way so that support geometry can be physically removed. 10. and that all objects are closed and manifold, then you are ready to export. Go to the top viewport. Click and drag from left to right to select your workbed boundary as well as all objects within. Type and enter export. Make sure to select the file type STL, which is an abbreviation for stereolithography. Exporting to this file format will create an automatically meshed version of your model and will include only the actual vertex positions for each meshed triangle for each object, and will exclude any UV data, vertex color data, material data, and any other data which would be irrelevant for 3D printing. It will also exclude any non-3D geometry, such as our workbed boundary curve, so it does not matter that it is selected prior to export. Make sure that the file name for the exported STL file is precisely as follows: your first name. So in my case, Alexander. It's simple as that, unless you have prepared several workbeds which you will export separately, one exported file per individual workbed. In that case, make sure that the file name is your first name underscore part X, where X is the part number, that is the number or index of the exported workbed. So in my case, Alexander underscore part 1. Click save to continue. The tolerance, that is the maximum distance between the generated mesh and the original BREP geometry, should be set to 0.01 millimeters. 1/100th of a millimeter is suitable for 3D printing here. Click OK to continue. File type should be set to binary, and regarding the export open objects option here, keep it checked, since if any object would not be properly closed and manifold, then we get that error in the slicing software, and we can notify you of that for you to fix, instead of omitting any open objects during export and being surprised afterwards that it was not printed. Click OK to export the file. If you would have more than one prepared workbed to export, repeat the previous steps for each workbed, one exported file per each prepared workbed. Send us the file or files via email. Send one email with both Henrik and me, Alexander, as recipients. Including us both will reduce the risk of your request not being noticed if one of us is ill or otherwise absent, and will also make it easier for us to maintain a queue. Make sure that the subject contains the word 3D print. We have an automatic filter for this. Include your STL file or files as attachments to the email. Do not include any Rhino file. In the contents of the email, make sure to state if there are several files to be 3D printed. It can be good also to state any date before which the 3D print has to be finished. A situation where this would be beneficial would be when there is a queue, and there is no possibility for your 3D print to be finished before the stated date. Then we can simply reply with that information, so that you can decide upon an alternative fabrication method. Usually, there is only a queue 2 to 3 weeks before the diploma thesis mid-seminar and final seminar, so if you are able to plan your 3D printing ahead, it is wise to avoid these hotspots. The queue system is intended to be as fair as possible, in a first-come, first-served way. Don't expect priority due to your project being more important than any other students. Instead, make sure to send us the file in good time so that it is finished in due time. However, on our very own initiative, the queue order is a little flexible, because we only initiate 3D prints during the workday, and if one particular print takes 14 hours and another one 4 hours, then the 14-hour print cannot possibly be ready for collection any earlier than the next workday. But the 4-hour print can be fully 3D printed within one workday and still leave time for us to initiate the 14-hour print on the same machine. And that will still be done before the morning after, with the only difference being that we could complete 2 prints instead of 1. In such a case, we are a little flexible with the queue. If you have several workbeds to print, then usually you will have to, so to say, queue after yourself. So that the first workbed, or perhaps depending on current demand, your 2 first workbeds will be initiated, and then the 3rd and 4th will only be initiated after workbed 1 and 2 are finished, and so on, to reduce the risk of one student blocking the usage of most of our 6 3D printers, the 6 of which should accommodate 600 to 650 students. We hope that this tutorial will make your experience of 3D printing within the context of the model workshop, KTH School of Architecture, an endeavour more clearly approached, and with the prerequisites more accurately described than what has been before. We thank you for your time.